Number 3, there's a load, right? And then finally, this is your last part, 4. So you have to divide into 4 sections. Okay. So now we are going to calculate. We're going to calculate delta L. Okay, delta L due to the actual what? Loading. Okay, and we remove, right? We remove the support at point what? We remove the support at point B. Okay, so deflection of 1. Right? So 1, now you have to recall the hangman theory, right? So if I hang you by your neck, which you don't have your arms to support, you are going to feel the 300 and 600, and the 300 and 600 is going to induce tensile. So positive means tensile. So P, the length is equal to 0.15 divided by the cross-sectional area. The cross-sectional area is 250 times 10 to the power minus 6, and all of them are made of steel, or we make of a common Young's modulus. Okay, so again, I highlight that this is made of a single material, so we just divide by what? E. Okay, so when you calculate this, this will be equal to 900 power of 3 times 0.15 divided by 250 power minus 250 power minus 6. So it's equal to 540 positive 540 times 10 to the power 6 divided by E. The positive down here means it's going to be what? Tensile. Okay. And then now we're going to calculate the deflection at section 2. So deflection at section 2, we don't need to consider the what? 300, right? Because the 300 has been taken up by section number 1. So section number 2, we only need to consider the 600 multiplied by 0.15. Cross-sectional area is again the same, 250 times 10 to the power minus 6 divided by Young's modulus E. All of them, again, I repeat, is made of a common material. So 600 power 3 times 0.15 divided by 250 power minus 6 is equal to 360 times 10 to the power 6 divided by E. Right, it's positive over here because it is what? In tensile. Right, then deflection at point 3. The load carried is 600. Length again 0.15 divided by cross-sectional area is now 400 times 10 to the power minus 6, and then E. Okay, so this will be equal to 600 power 3 times 0.15 divided by 400 power minus 6 is equal to 210. No, I did something. 600 power 3 times 0.15 divided by 400 power minus 6 is equal to 225 times 10 to the power 6 positive is going to be tensile. And finally, deflection of section 4. So this is carrying 0 load. It's not going to see the 600 because 600 is carried up between C and K, right? K and B is not going to see the 600 at all. Okay, so multiply by 0.15. So I'm still using the hangman theory that I taught last week. So this will be equal to what? 0. Okay, so from here, we're going to add up everything. So the deflection due to the load is equal to 540 times 10 to the power minus 6 divided by E, and then plus by 360 times 10 to the power 6 divided by E, Young's modulus, plus by 225 times 10 to the power 6 divided by Young's modulus. Okay, so 540 plus 360 plus 225. So it's equal to 1125 times 10 to the power 6 divided by Young's modulus E. Okay, So this is going to be positive. Positive means it's going to be what? In under tensile. Okay. So this is step number 1. Okay. So we're going to look at step number 2. So step number 2 is we're going to introduce a redundant load right? We're going to introduce a redundant load at point B, and we're going to also apply that the deflection due to the load plus by the deflection due to the redundant load must be equal to what? Must be equal to 0. Yes. Okay. So I'm going to again get the image. Okay. So the diagram will be a bit messy now. Okay, I'm going to wipe out things. I'm going to wipe out. So we still know that there is still no support down here. We know that. Okay. Right. So like what I taught earlier, right? Like what you guys have seen earlier. What do you guys say? We are going to add the redundant member, right? And we don't need to consider the actual load of 300 and 600. Okay. So we are going to introduce a redundant load at point B. Okay. So over here, we're going to introduce a redundant load. All right. So we're going to put a redundant load. And we call this RB. Okay. We're going to call this RB. Right. At this stage, what we're going to do now is we don't need to consider this. No need to consider this load. Because we already consider it in step number 1 already. Okay, you don't double dip, double dipping, right? Double dipping, it will not work out at all. Okay, so when you introduce a redundant load, you can get rid of this. Okay, so when this is the case, how many sections are there now? Now we don't have redundant load. Can someone tell me how many sections we have now? Anyone?
2.
Yep. Yeah. So it's only the change in what? Area, right? Well done. Okay, so we only have 2 redundant loads. So this is 1, right? And this is our what? 2. Yes or no? Okay. So there's our 1 and there's our 2. Now, the next thing I want you all to take note is what? The redundant load will be inducing what load on our system? Is it a tensile loading or compression loading? Anyone?
Compression.
Yep. So you're absolutely right. So the redundant load is going to induce a compression load, right? So when that's the case, you can directly put this down already. So delta R is equal to, so section 1, right? So what is section 1 going to feel? Is section 1 going to feel RB or no?
Yes, it will.
It will, right? Remember I taught you guys the what? Hangman, right? Now, if I'm going to push my hand on your feet, right? You feel relief, yes or no? Right? Your whole body is going to feel relief. Let's say you're hanging, then I'm going to put my hands on your foot of your toe, right? Or your feet. All your joints are relieved due to your weight, right? So RB is going to be felt in both section 1 and section what? 2, right? So section 1, so you have minus RB, right? So this is for section 1. So the length is equal to 0.3 meter. The cross-sectional area is equal to 250 times 10 to the power minus 6, and then the whole thing E. So this over here, so this is for section 1. right? And then you do a plus, but it's going to feel the what? Negative again. Okay, so this is for section 2. The length is the same, right? Divide by 400 times 10 to the power minus 6 multiplied by E. Okay, so this will be your what? This will be a section 2. Okay, so you do the math. So 0.3 divided by 250 power minus 6, right? 0.3 divided by 250 power minus 6 is equal to 1200 minus 1200 over E plus by 0.3, 400 divided by power minus 6 is equal to minus 750. Sorry, RB. My RB is missing. So minus 750, right? RB over E. So this will be equal to 1200 plus 750. So it's equal to minus 1950 RB over E. Okay. So now once you have here, what we need to do now, we need to apply the equation where delta L plus by delta R is equal to 0. Okay, so delta L we calculated earlier is equal to 1125 times 10 to the power 6. So it's equal to 1125 times 10 to the power 6 over E. So this will be equal to this is plus and then minus 1950 RB over E, right? And then the whole thing will be equal to what? 0. Remember what I told you guys, right? This is due to delta L, right? Is in one direction, and delta R is in the opposite what? Direction. Okay, so you have to take note. Okay, we are getting both as positive means your analysis is flawed. Okay, so from here, we know that RB, from here, we know that RB is equal to 1125 times 10 to the power 6 divided by the Young's modulus, divided by 1950. So the Young's modulus can be cancelled, right? Can be factored out, so you don't need the Young's modulus. So this is equal to 1125 power 6 divided by 1950. So this is equal to, I get 576. Okay, 576.923 times 10 to the power 3, right? Times 10 to the power 3 Newton. And the answer is positive, so it's going what? Upwards. Okay. Now, so from here, right? From here, you want to find the reaction at point A. Okay, so I'm going to start on another page. I'm going to copy this diagram first. Anyone, any questions so far?
Sir, I just have a question. Where you got the number 1200 RB minus 750 RB? Where did those two numbers come from?
So I did this calculation. Right? So 0.3 divided by 250 times 10 to the power 6. Hello? Does that make sense?
Yeah, that makes much more sense.
Yeah, answer me, okay? When I answer, tell me yes or no, okay? Don't make me wait, you cheeky son. Right, okay? Okay, so we know that this is... Okay, now, let's go back to our... I'm going to copy this diagram. So what I want to find now... Wait. Copy. Right? So now, we're going to find the reaction. Right? at point A. Okay. So if I'm going to remove the support now, okay, we're going to draw our free body diagram.